Let's do another application of our stronger version of Fubini's theorem. So let's integrate the function 1 minus 2x over the region D, where D is a triangle with vertices at 0, 0, 2, 3, and 5, 3. So before we do anything else, let's draw a picture here, and hopefully the picture will show us whether we want to slice this horizontally or vertically. So vertex at 0, 0. Vertex at the point 2, 3. Vertex at the point 5, 3. And so we have this triangle here. So the question here is, do we want to slice this horizontally or vertically? If we slice this vertically, realize that, here we have top function minus this bottom function, but right there, x is equal to 2, x is equal to 2, the top function changes from this line to that line. And so if we wanted to try to slice this vertically, integrating, doing a vertically simple region here, we'd have to break this into two parts. That seems complicated. So instead, what we want to do is realize that this is also a horizontally simple region. It'll be much simpler for us to integrate using horizontal slices. We can already see here that y runs from 0 to 3. And so then for fixed value of y, x runs from here to here. We just need to figure out this, an equation for this line, an equation for this line, and write them as y in terms of x. Okay, so how do we do that? Well, this line right here, I'm just going to pick this one to do first. This is a line that passes through the origin, and it has slope. When x goes up 5, y goes up 3. So an equation of this line would be y is equal to 3/5 x. When x goes over 5, y goes up 3. So the slope here is 3 over 5. We wrote y in terms of x, but we don't want y in terms of x. We want x in terms of y. And we just multiply by 5/3 on both sides. X is 5/3 y. And so this is going to be our upper bound here on x is 5/3 y. Similarly, this one is going to be, this line right here is y is equal to 3/2 x. The slope of this line right here goes through the origin, and the slope is y, x goes over 2, y goes up 3, so 3/2. But this is y is equal to 2/3, x is equal to 2/3 y. And so this right here is going to be, these are our bounds here on x. So what do we say? This double integral is equal to the iterated integral. Y runs from 0 to 3. X runs from 2/3 y to 5/3 y. And our integrand is 1 minus 2x dx dy. We begin, so this is the setup. The setup is almost always the more interesting part. To evaluate this, we look at the inside integral here first. And so we get the antiderivative here will be x minus x squared. Thing that we're plugging in is x is 2/3 y, x is 5/3 y. Oops, I wrote dx twice there. That should be a dy. And so when we plop in these things, we end up with the integral from y is equal to 0 to 3 of, okay, so when we plop in x is equal to 5/3 y. We have 5/3 y minus 25/9 y squared minus, now we plop in 2/3 y. 2/3 y minus 4/9 y squared dy. We can simplify the thing inside of these parentheses. We have 5/3 y minus 2/3 y, that's just y. And then we have a negative 25/9 y squared plus 4/9 y squared minus 21/9 y squared dy. At this point, it's a very easy integral to evaluate. Y squared over 2 minus 7/9 y cubed. Plug in 0 to 3, and you get negative 33/2. So the moral of the story here is think about carefully which way allows you, in this case, slicing horizontally, which is probably not our default instinct. Our default instinct is usually slice things vertically, not horizontally, but slicing this horizontally allows us to do this with one integration, not two. Okay, here is a pre-class problem for you to try. It's very similar to the one we did, not in this video, but in the previous couple videos. Integrate f of xy is equal to x over the region bounded by y is equal to x squared and y is equal to x plus 2.